Academy of Science. I'm sorry, it's difficult for me to say the name.
No problem. Thank you, Chair. And my name is Weiwei from Research Center for Eco-Environment Science, Chinese Academy of Sciences. And I would like to thank Professor He for inviting me here to introduce my work. And my major is not about membrane, but my major is about detection and identification of micropollutants and study the fate of the micropollutants in the aquatic environment. And if my work research can provide some reference for you to choose the micropollutants for membrane removal, it will be my pleasure. So today I will introduce the three parts. The first one is if we have a target compound, we want to determine a concentration. So we can develop a high sensitivity quantification method for these target compounds. Usually we use the solid phase extraction for pretreatment procedure, and then we use the UPLC mass spectrometry to identify them. And based on this developed method, we can study the occurrence of this kind of micropollutants in different kind of aquatic environment samples, like surface water, like wastewater. And the second part is if we don't know, we are not sure. We are not sure what's the compounds in a water sample. For example, in wastewater treatment plant, some compounds go through the entire treatment process. We call them refractory pollutants, but we don't know what are them. So if in this case we can develop some method for component profiling of these pollutants, and based on this method, we can characterization of this compound in wastewater. And in the end of my presentation, I will also introduce some future perspective for analyzing micropollutants, like the non-target screen method. So the widely distribution of micropollutants in the environment has become a global environment problem. So this figure shows that a large amount of data has been reported around the world. So maybe in European area and in China, we have published a lot of paper, right? And some micropollutants attract increasing attention, like the red color show the PPS, the blue color shows pesticides, and the green color shows the PFAS. And in China, antibiotics and estrogens has been receiving considerable attention. And in this paper, every year we mention a lot of this kind of compounds to the environment. And as a result, the high river basin in Beijing, Tianjin, Hebei region, as well as the Yangtze River and the Peel River basins are all hotspots for pollution by micropollutants. And the research and control of micropollutants has gone through some stages. First, the environmental exposure to micropollutants has been reported around the world in the surface water or even in the drink water. Then in some area, for example, in European Union, they launched a watch list to determine some high risk pharmaceuticals in the surface water around the European area. And for the important pollution source of the micropollutants, the researchers and some, the researchers has tried their efforts to upgrade the wastewater treatment process for removing these micropollutants. So, for example, in Switzerland, they have launched a regulation to upgrade the treatment processes in wastewater treatment plants, and the process must remove the pharmaceuticals by above 90% from the wastewater. And in China, in 2022, where our government launched an action plan for the control of emerging pollutants such as antibiotics, PFOS. So first, for the environment samples, there are some problems for determining the concentration of micropollutants. The first one is their concentration is always in very trace river, right? So we should use solid phase extraction to concentrate them. The second problem is the background matrix is very complex. So this SPE is also can purify the samples. So if we got solid samples, we use the USE before the SPE to get the concentrate sample. Then we go through the instrument analysis. So from these figures, we can have some good resolution, high resolution for different categories of micropollutants, include PPCPS and their metabolites, and EDCAS, as well as their conjugates and some PFOS. So based on this developed methods, we apply this developed method. The first example is we studied the occurrence of PPCPS in surface water. This figure shows the map of Weiwei River. Weiwei River is belonging to the high river system, and it goes through the Beijing city, the Hebei province, and the Tianjin city. So it's not just the result of the PPCPS concentration in this river is not just let us to know the pollution level. We can see the adjacent land use table is different along this river. The up here is the mountain area, then urban area, then agricultural area. So this data also can analyze what's the effects of the adjacent land use tab on the pollution level of PPCPS in the river. And as a result, the result shows 22 pharmaceuticals have been detected, and some sulfonamide antibiotics, and some caffeine has been detected with high frequency, and the highest concentration is caffeine, and it's about 2 microgram per liter. And we should notice that some compounds have been detected at a very high concentration, which is approaching the effect concentration about some aquatic organisms. So let's see the impacts of land use tab on the concentration. We can see the urban area, the agricultural area, they have high concentration of PPCPS comparing to the mountain area, and the agriculture area always have high concentration, means there are some wider range of pollution source spread in this river. And the other application case is the occurrence of micropollutants in wastewater treatment plants. So we can collect the water sample from the WWTPs located around China. And the result shows the concentration level of ppCPS is about is on the nanogram per liter, or when they are very high, they will be microgram per liter. And within the EDC type, the estrogens is always in very low concentration, but the phenolic EDCS, that means bisphenol or nanophenol, their concentration will be very high, maybe higher than other compounds by 1 or 2 orders of magnitude. And the PFOS shows high detection frequency and the average concentration around 30 nanogram per liter. There also shows some different regional differences. And let's say the section, which section of the WWTPs has high removal efficiency for this compound. The biological treatment process have high removal efficiency for ppCPS, EDCS, and sometimes for PFOS. The convention treatment technology like coagulation, sedimentation shows very limited removal efficiency for this compound. But if we use some advanced technology like ozone, like BAC, their removal efficiency can be significantly improved. But for PFOS, it's not a good result. So usually we pay attention to the compound in their free form, I mean in their parent form, but in the aquatic environment samples, they always exist in other form. This is an example for estrogen. They have other conjugate form. And if we detect the free form and the conjugate form in the wastewater, we can see for some estrogen, the conjugate form can be the major form in the total amount. And we also can find that the wastewater treatment processes can remove free form, but not very efficiency. In fact, not very good for removing the conjugate form. And there is some other example for sulfonamides and CBZ. And we also can see their conjugate ratio is very high. So that means if we just determine the parent form or the free form of this kind of compounds, we may underestimate their concentration or their risk of this compound in the water sample. And we should note some of these conjugated form can hardly be removed by the treatment processes. And what about the drinking water treatment process? There are two examples. We can see the PFOS always has a high concentration than the pesticides and antibiotics. And the drinking water treatment process is relatively effective in removing pesticides and antibiotics, but not good for the PFOS. So the main removal stage for these micropollutants is sand filtration and activated carbon processes. So if we don't if we are not sure what kind of compounds existing in the wastewater, we can have a instrument system for identification of the components. So we use the resin fracturation rate and divide them based on hydrophility and hydrophilicity. And we use EEM, UV, and XPS to determine their functional group and the molecular weight, these characteristics. And we use this method to classification of organic compounds in wastewater. We want to know what kind of components contributing to the color. So the result shows the organic matter in the effluent is mainly composed of this HPOA fraction and following by the HPI fraction. And based on the some other instrument analysis and correlation analysis, we can find organic compounds with molecular weights of 2 to 3 kilodalton is the main contributing components to chromaticity. And then also we can find among the main fracturation with the humic-like substance exhibit the highest intensity, fluorescence response intensity. So it's the main substance contributing the color. And if we study the treatment processes to remove the DOC and the chromaticity in the wastewater, we can see the conventional tertiary treatment process like coagulation and UV cannot remove them. But if we use the HCl2, they can oxide some of them. So we also tried the non-targeted identification method to determine the pollutants in water. And this analysis is based on the instrument high resolution mass spectrometer. So this spectrometer can provide a large amount of the fraction information of the mass to ratio information. And based on this information, we can have the group. We can have the group information, and we can tentatively to infer what kind of the chemical compounds. And then we can use a library to categorize this compound into 5 levels of certainty based on their confidence. But if we want to make sure the components by 100% certainty, we need a reference standard. And we use this method for determining the pollutants in drinking water surface. And this figure, the Y coordinate is the name of the specific compound, and the X coordinate is the toxicity type based on the EPA toxicity assessment model. And in both of these two water resources, we can see some common substance exist here, like the plasticizers, like the fungicide, like a PAHS, and there are also some specific substance is also like include the fungicide, the herbicides. So if we study the performance of the DWTPs on removing these compounds, we can see that the PP, CPS, and the EDCS can have high removal efficiency by the treatment process, but some pesticides have still remain in the influence of these compounds. So this is a summary. So based on our above work, we may have some micropollutants of concern. So first is, as we think we don't, we can't only, pay attention to just the parent form or free form. We also should pay attention to the conjugate form and metabolites of these micropollutants. And then the humic-like substance is very hardly removed by the drinking water or wastewater treatment process. Then for specific micropollutants, the PFOS, the pesticides, fungicide is widely spread in the water sources and cannot effectively removed by the treatment plant. So, okay, these are my results, and if this can provide some reference for you.